Welcome back to the videos. Today we are again going to talk about matrix multiplication, and specifically we're going to sum up some rules of matrix multiplication. So our topic today is rules of matrix multiplication. I'm just going to put all of these rules into a theorem. First rule is this matrix multiplication that we defined may look a little strange, and we have already seen that it behaves strangely in some aspects. In particular, it's not commutative. You can't just change the order and not change the result usually. And we have also seen that it might produce a zero matrix even if you multiply two matrices that are both non-zero. That's unusual for a multiplication. On the other hand, it shares some nice properties with the usual multiplication. And one of those is it's associative. So if you multiply three matrices, then it doesn't matter whether you multiply the first two and then with a second and with a third one, or whether you multiply the second and the third and then with the first one. You cannot change the order of those three, but you can change the order of evaluation. So to make that more precise, let's say we have matrices A in R to the M by Q, B in R to the Q by N, so we can multiply A times B. And let's take a third one and we call it C. And we multiply B times C. So we need C to be in N to the something like P here, N by P. And for that setting we have, well, the product A times B times C. If I first evaluate this AB, I'm getting an M by N matrix, and I can then multiply by C to get an M by P matrix. And associativity means that is the same thing as taking first these two matrices here. So if I first multiply B and C, and then A times the result, that will yield the same result. I'm not changing the order. A is always the leftmost matrix, C is always the rightmost, B is always in the middle. So that is associativity. And basically that means we can do without braces. It's not really important where they are, and we can make a choice which of these matrix products we want to evaluate first, whichever is easier for us. Second property, we've already met the identity matrix, and it turns out that name is just defined because the identity matrix is a neutral element of multiplication. And it doesn't matter whether you multiply from the left or from the right, as long as you get the dimension right. It's always a neutral element. If the matrix in the middle, of course, is not going to be changed, meaning if that is a square matrix. Otherwise, we would always change the number of rows or of columns of that matrix. So the identity matrix is a neutral element for matrix multiplication. Meaning, for a square matrix A in R to the n by n, we have A times In is A, and also In times A is A. Multiplying by an identity matrix does not change the matrix. Third property, also a property that we usually want for a multiplication, where we also have an addition. That is, we usually want these operations to be distributive. And let me just write down what that means. It's easier to see, I guess. So what I want is matrix multiplication is distributive, and to be precise, that is two properties that are very similar. So the first is, let's say we have a matrix A in R to the m by q, and we have matrices B1, B2 in R to the q by n. So we can multiply A times B1 or A times B2. And then this distributive property is, well, if I multiply A by the sum of those two, B1 and B2, that's the same thing as multiplying A by B1 first and then adding A times B2. And of course, this here is only distributive property on one side. We also want this on the other side. And because matrix multiplication does not usually commute, you can't just change the order, we have to write down that second property separately. But that also holds. So for A1, A2 in R to the m by q, and B in R to the q by n, we have A1 plus A2 times B is A1B plus A2B. So that's the distributive property. Part 4. One other operation that we have for matrices, apart from addition and now multiplication, is we can multiply matrices with a scalar. That's one of the first operations that we introduced. And of course, we want this operation to also be compatible with matrix multiplication. And it turns out it is. So what do I mean by compatible? Well, I mean, if I multiply two matrices, let's call them A and B. So I have A in R to the m by q, and B in R to the q by n. And let's take a scalar, lambda in R. And for that setup, we have, well, we could multiply lambda with the product of A and B. And what I want is this multiplication does the same thing as multiplying lambda with A first, and then multiplying the result by B. And that in turn should do the same thing as multiplying A with lambda times B. Right? So I can put the lambda wherever I want. It's always the same result. And of course that also holds. And this property is called homogeneity, by the way. And finally, let's talk about transposition and ranks and matrix multiplication. That's going to be the last two properties here. The first one is on the compatibility of multiplication and transposition, and that's a little strange. It's not as you would hopefully imagine. So if you transpose the product of two matrices and compare that with the product of the two transposed matrices, that is usually different, unfortunately. But it's almost true. You just have to reverse the order. So what happens here is transposition reverses the order of multiplication. So what we get here is the following. For A in R to the M by Q and B in R to the Q by N, we have that A times B transposed is the same as B transposed times A transposed. So if you want to distribute that transposition onto the single matrices, then you have to reverse the order of your matrix product. And the last point, let's talk about the ranks quickly. So let's say we have two matrices again, A in R to the M by Q and B in R to the Q by N. Then the question is, can we say something about the rank of A times B? And the answer is yes, we can, of course, say something about the rank. We have already seen that multiplying A with one vector can be seen as a linear combination of the columns of A. And what A times B does is basically it takes linear combinations of the columns of A and composes the columns of the result this way. So each column of the result is a different linear combination of the columns of A. And that means, of course, there cannot be more linearly independent columns in the result than there were in A. In other words, the rank of the result cannot be higher than that of A. And of course, the same argument can be done about the rows of B. So basically what A times B does is it's a linear combination of the rows of B, or each row is a linear combination of the rows of B. And again, that means the rank cannot increase above that of B because the result cannot contain more linearly independent rows than B already has. So the rank of the product is always less or equal to both the rank of A and the rank of B. And that means it's less or equal than the minimum of rank A and rank B. In other words, matrix multiplication can only decrease the rank and never increase it. So that concludes this list of properties of matrix multiplication that you should bear in mind and that you will apply in many, many different contexts when actually doing matrix multiplication computations. In the upcoming videos, we'll have a look at a few applications, and then we'll dig a little deeper into this matrix multiplication idea by having a look at inverse matrices. I'll see you then.